Today I'll be talking about evolutionary and genetic algorithms. So these algorithms are based on concepts of natural selection in biology, and that states that organisms that best fit their environment are more likely to survive and reproduce. These organisms will have traits that help them survive their environment, and these traits are passed down through generations, and with enough time, entire species can change to have some of these adaptations. So one of the more famous examples is Charles Darwin looking at finches and how food availability can change the size and shape of their beaks. So for algorithms, we can think of each solution as being an individual organism. We generate many solutions, and then the best ones are used to come up with more solutions. And then the best parts of each solutions are carried over through new generations, like the genetics of animals. So this is the process of training a genetic algorithm. So for the very first generation, we will create a number of random solutions. We'll take each of those solutions and then verify them against some criteria, and then we'll pick the best n% of those solutions that we will carry over. And the criteria could be something like which solution works the fastest, survives the longest, highest score, anything that you want to minimize or maximize. So we'll use that information from the surviving solutions to make new ones. And the algorithm for that can be adapted based on what kind of data. So you might take the average of two solutions, or carry over which parts of the solutions are the same. And we also apply mutations, and then this process is repeated over and over until you stop showing improvement or the solution is good enough. So considerations that need to be made is the size of the generation. That can affect how fast the algorithm can train, how many you want to survive each generation, and how much mutation there is added between generations. And so the reason why mutation is important is we want to avoid local minimums or maximums. So say if this is the criteria we're testing against, we're finding solutions like among here. These can keep driving down until we get to here, but that is not the best possible time we could have. This is just a local minimum, so we want to find the global minimum. And so without mutation, we're only going to have solutions here if we have them at the beginning. But with mutation, we'll have a few outliers in every generation, and hopefully they would start getting faster than the path that the generation is going down, and eventually would shift over to finding solutions over here. So one area that I've seen these genetic algorithms used is software fuzz testing. So the basic idea of fuzzing is you'll repeatedly try running some software with different inputs, and if we keep doing that over and over with valid and invalid inputs, eventually we will find some bugs in our code. So a lot of these are considered dumb fuzzers, and those are ones that don't take any feedback. So a common way is just to take a valid input or a valid file and make small changes to it to see how the code behaves. or just randomly creating new data. So a genetic fuzzer will actually be able to take feedback from the target software, and it can use the genetic fuzzing algorithms to try to maximize code coverage. What that means is just how many lines of code is run per execution. So the input for the target program is what we will evolve, and it's commonly used in Google's AFL, shown over here. You can see here it's measuring coverage, new paths, and new edges, and that's what we will try to maximize. So code like this on the left really illustrates why genetic fuzzing can work a lot better than many of the other methods. So here we have some very nested if statements. So this program will take up to 16 characters, and then it checks through the first 8, and if it's A through H, it hits this code which causes a crash. Otherwise it just returns normally. And so with like a random strategy or like incremental, there is a 1 in 26 to the 8th chance of crashing this. If you're able to manage 5,000 attempts per second, I calculated that it would be over 483 days of constantly running this code to get the crash. Now with genetic fuzzing, it will learn where it needs to put certain letters to increase coverage over time. So eventually it'll learn that it always needs to be an A to get any increase in coverage, and then B, C. We can incrementally make progress through all of these if statements towards the crash. And running this on my own system, it found the crash in about 5 minutes. So the video you're seeing now is that same AFL algorithm previously discussed, how it was adapted to play Super Mario. So this is using code coverage, and then along with some human and annotations added to the code, so they can steer the behavior of the AI. And then the controls are from an input file, and so the character will always move right, and then each time slice it can either take an action or not. And so that pattern is what AFL is fuzzing. And I included this because it really shows the power of the algorithm in AFL. A lot of people in the machine learning industry community don't really think of genetic or evolutionary algorithms as being that powerful, but this is a case where they work very well for their application. They're very fast. You don't need a lot of data about the environment or anything. You can figure that out on its own. So for something like AFL, a neural network would not be a good choice, because training it with back propagation would be way too slow for a fuzzer. With the fuzzer, you want as much CPU time going to actually testing the application. A neural network would take too much of that time training. So in this case, a genetic algorithm is a much better choice. So one other project that was also adapted to playing Super Mario is this NEAT algorithm. It stands for Neural Evolution of Augmenting Topologies. So the idea is it can train neural networks through this evolution algorithm. So each network is a solution to the problem, and this will change both the structure and the values of neurons. You can add or delete neurons, or add and delete connections. So on the right here, this neural network just started as the input over here, which is data about the environment, and then these neurons that correspond to button presses, and then the rest of these connections and neurons were all placed through this evolution